Alright, this is your 5.4 notes, the mean and standard deviation of the binomial distribution. So we've talked about the mean and standard deviation of how to find that for a discrete probability distribution in the last section, or in 5.2. But for the binomial distribution, it's much simpler to compute. So remember, this is our notation for the mean of a random variable. This is our notation for the standard deviation of that random variable. So for a binomial random variable, it's simply just n times p, okay? And for a standard deviation, it's the square root of n times p times q. Remember, q is 1 minus p. And if you think about it, n times p, since that is the mean, we could just write this as just the mean times q, and then take the square root, if you want to think of it that way. I don't know what's up with this, why everything's off the screen. But anyway, there's your definitions. So if we're ever asked to find the mean, well, the mean of this random variable is n times p. N is equal to 100. P is equal to 0.21. So n times p is 21. And then if we wanted to find the standard deviation, we would just take n, which is 21, multiply that by q, or sorry, n times p, which is 21, multiply that by q. Q is 1 minus p, so that would be 0.79, and then take that square root. So square root of 21 times 0.79 equals that. Or again, I could say, if I wanted to use the entire formula, n times p times q, 100 times 0.21 times 0.79, and you get the same thing. I'm just showing you that if you just plugged in and did the formula rather than use that shortcut where you plug the mean in there, you end up getting the same thing. So I get 4.073. Now what could I use this with? I could come up with rare events. Remember, if I go to 21 plus and minus 2 standard deviations from the mean, that's a cutoff for things that are rare. So if I did 4.073, double that, add and subtract from 21, then I get the values that I consider rare in this distribution. So 21 plus, well, let's do minus first, minus 2 times 4.073, and then change that minus to a plus. Alright, so 21.85 or 12.854 all the way up to 29.146. Right, that's an interval. So anything in there is usual or not rare. And then anything outside of that would be considered rare. Okay, now these are discrete values, so obviously it would be, anything like 12 or below, 30 or above. If I had a sample that had 33 of these orange candies in it, that would be considered rare. That shouldn't happen very often. If I have a sample that had 10 in there, that should also be rare. Okay, so once we get the mean and standard deviation, we can do things like we've done before. Find out what constitutes a rare event in these specific cases. Alright, past election voter turnout was 55%. A survey, 866 subjects asked if they voted in the election. Find the mean and standard deviation for voters in these groups, 866. Alright, so again, this is binomial. Again, under the assumption of independence because of this. So let's go, the mean is n times p. N is 866 in this case, and p is the probability of a voter that they turned out and voted. So 55% is a decimal, is 0.55, and I multiply that out. So 866 times 0.55 is 476.3. Alright, and then the standard deviation is the square root of n times p times x, or sorry, n times p times q. Alright, and again, n times p we just computed right there. So if I multiply that by q, which is 1 minus p, so that would be 0.45 in this case. Alright, and then took the square root of that. So that's 14 point, the 2 decimal places this time, 0.64. Okay, and then it says 437 in the survey of 866 people, 437 said they voted in the election. Is this result consistent with the turnout, or is this result unlikely to occur if the turnout really is 55%? So what we can do, a couple different things. One, we can look at how many standard deviations that number is away. So 476.3, if I subtract 2 of these 14.64s, .3. Notice the last thing I did was that standard deviation, so I'm going to do minus 2 of those. So I'm going to hit second. The negative symbol second is answer. Hit enter. So 447.02. So it's about 447. Right. That's 2 standard deviations below the mean. That's a cutoff for rare. That would be pretty rare. Alright, but another way we could do it is the binomial CDF, because in reality, what we should do here is look at the likelihood of seeing something this far away from the mean or further. Alright, we talked about that in one of the last videos. So this is the binomial CDF that does that for me. Oops, second distribution. Binomial CDF, right? N is 866, P is 0.55, and then our number that we're going to stop at is 437. So the probability of seeing from 0 voters to turn out all the way up to 437 is what we're computing here, is only a 0.4% chance of happening. Alright, and since that's such a low chance of happening, then we would conclude, so this is part A. Alright, part B, is this result consistent with the data? No. That value 437 is more than 2 standard deviations below the mean. So that means it would be rare if this were true, if the 55% were true. Alright, but the other thing is it's rare by the binomial distribution also. So the probability that the voter turnout was less than or equal to 437 what we just found in our calculator was 0.004. So both of those are saying that this is rare. More than 2 standard deviations and the 0.004. Both of those are saying that this was a rare scenario. So both of those answer B. And then C, based on these results, does it appear accurate that voting results can be obtained by asking voters how they acted? No. Alright. No, you can't, but we can also, what we're going to do in the future is question the validity of that percentage. Okay? That would seriously, if I saw this number this low, that would seriously make me think there's something wrong with this, under the assumption that these people are telling the truth. Alright, that's what C's getting at, though. It's probably not a good method of just asking people, did you vote? Alright, so those are some questions in 5.4. Just remember the formulas for the mean, n times p, and the standard deviation. Those are the shortcut formulas if you have a binomial random variable.